In this video, we're going to show you how to do U substitution with a slightly different strategy, which some students find a little bit easier to use. It works well for almost everything we do this year, so if you like it better, you can choose to use this method instead. It starts off the same way though. We still need to look for the setup where we have an inside function whose derivative is in the outside. Remember, when we say the derivative is on the outside, the coefficient of the derivative doesn't have to be there, but everything else needs to be there exactly right. So in this case, the 4x cubed will be our inside function. The 9x squared is its derivative, pretty much. So we can set it up what it looks like. Our u is 4x cubed, and du dx is 12x squared, which again, it's not exactly what we have there, but the x squared is all that we need, so we can fix the rest. In the other strategy for doing u substitution, I got the du by itself, and we would do a substitution with that. A slightly different strategy, though it amounts to the same thing in the end, is to get the dx by itself, which means moving the dx over here and bringing the 12x squared over there. So that would be 12x squared is equal to du over 12x squared. Sorry, dx is equal to du over 12x squared. And so the substitution that we're going to do, we're going to put the u in for the 4x cubed, and we're going to put the du dx in where we see a dx. Sorry, we're going to put du over 12x squared where we see the dx. So we're going to do those two substitutions. The advantage to this strategy is you don't have to fix the coefficients first. So when I rewrite this, the 9x squared, I'm not doing anything with it quite yet, but the dx I'm going to turn into du over 12x squared. And also in the denominator is the secant of u. So notice what happened is we put the du dx in. We also put the u in. Sorry, I said it again. We put the du over 12x squared in. We also put the u in. Those are the substitutions that we did. And now what we do, instead of fixing the coefficient in advance, we make this substitution, and now we just simplify what's in that integrand by taking the 9x squared and reducing it with the 12x squared. 9x squared over 12x squared is 3/4. The x squareds cancel out. Du over secant of u. Now I'm going to pull the 3/4 out of the integral. We can do that with coefficients. And the antiderivative of 1 over secant of u, I might not think I know it. It might not be one that I've memorized in that form. But 1 over secant of u is the same thing as cosine of u. So what we're looking at is 3/4 times the integral of cosine of u du, or 3/4 times the sine of u plus c, which we can turn into 3/4 times the sine of 4x cubed plus c. And what I'm saying is that is the antiderivative of 9x squared over secant of 4x cubed dx. So that would be my answer. One last quick note is we can check our answers also. I want you to be comfortable checking with Desmos. So the idea is that we are saying, look at that screen again, we are saying that the antiderivative of 9x squared over secant of 4x cubed dx is 3/4 times the sine of 4x cubed plus c, which means that the derivative of this is equal to that. The derivative of 3/4 sine of 4x cubed plus c, which means plus anything, is 9x squared over secant of 4x to the third. So we'll check that. Is that true? I'm going to make a function, give it a name, so that way we can use function notation and prime notation and all of that. I'm saying that 3/4 times the sine of 4x cubed, and I really don't care what the graph looks like quite yet. In fact, I'm going to turn it off. I don't want to look at the graph. don't want to look at the graph of that at all. At least not yet. I'm saying that its derivative, which is a little bit crazier than what we're used to seeing, but if I zoom a little bit, it's not quite that crazy anymore. I'm saying that that derivative is equal to our original integrand. So I'm going to compare that to 9x squared over the secant of 4x cubed. If those two things are the same thing, that means I'm correct. The derivative of my answer is the original integrand. Of course, I could put plus any number here. It doesn't change what the derivative is. That's the whole point of plus c.